Hello everyone, my name is Tianxing. Today I'm going to present our work entitled as DenseGATs, a graph attention-based network for nonlinear character deformation. In animation production, it is greatly important for animators to achieve the high quality of character deformation with complicated appearance. In this work, our motivation is to explore a deformation method to automatically compute deformations for new characters, thereby decreasing the time spent manual work. Most related work for deforming characters could be roughly classified into following groups. For geometry-based deformation, two well-known methods, LBS and DQS, are widely adopted in real-time applications due to the computational efficiency. However, they also suffer from the undesirable volume loss and joint budging artifacts. These artifacts need to be further manually fixed by highly skilled animators. This time-consuming process had to be repeated while deforming new characters. In contrast, physics-based method can achieve the convincing deformation effects by formulating the deformation process within a simulation framework. On the other hand, once the deformation parameters are specified, it is difficult to control the resulting shape of character in each animation frame. Furthermore, the physics-based deformation is computationally expensive and usually avoided in interactive applications. Learning-based deformation method try to learn the surface deformation as a function of designed parameters. For example, SMPL model can represent a wide range of human body shapes in varying poses. The parameters of the model are learned from the existing data, and the model could only be used for predicting the human body with fixed number of vertices. In the work of FDDA, they used feed-forward networks to approximate nonlinear deformations to achieve high accuracy while enabling real-time animation. However, once the networks are trained, they could only work for one specific character, and the application to new character is limited. Recently, neuroskinning addressed the model generalization problem by training a graph neural network. The trained network could predict skinning widths for production characters with varying number of vertices and bones. In this work, to address the above-mentioned problems, we propose a graph learning-based method to end-to-end predict offset adjustment of each vertex for nonlinear effects. Our proposed deformation method provides two key contributions. First, we explore an integrated deformation system which can directly result in complicated deformations for new animated characters by learning from the available artist-designed skinning features. It could greatly decrease the repeated manual work. However, learning such a huge amount of complicated features is not an easy task. Therefore, we additionally present a novel densely connected graph attention-based network named DenseGATs to achieve the goal of automatically generating nonlinear deformations. We adopt the idea of regarding deformations as a combination of linear and nonlinear parts. The mesh of the animated character is firstly roughly deformed by the linear-based method. The resulting deformations have visible errors, and we then use the network to produce the nonlinear corrections. These linear deformed meshes are parameterized with the graphs, which are then input into the network. We use various characters with different customizations in random poses for training and make the network possible for building the intricate relations. The trained networks directly output the corrective displacement of per vertex for the final nonlinear deformations. We use the formulation to conclude our pipeline. So given a character in rest pose, through the transformation S of each bone in the skeleton, we first use the linear basic method to deform the mesh. In this process, because skinning weights are directly computed without manual modification, the deformation result Ts is inaccurate and visibly different from the target deformation. To correct this difference, we further refine the linear-based deformation Ts based on its mesh graph G and generate the remaining nonlinear correction Hg. The final deformation could be expressed as Ts plus Hg. We next introduce how to construct the mesh graph G. We expect the input of our network to be the graph G, which stores features of vertices and edges. Here, V denotes the set of vertices, and E represents the edges. The adjacency matrix U indicates whether there is an edge between pairs of nodes. We next assign attributes to graph nodes. For one node, its attribute vector can be defined as Vi with 3 elements. Pi is the vertex position, Ni is the normal of vertex, and Si is the distance vector to all skeleton joints. In this way, Vi contains both mesh geometry information corresponding mesh vertex and the relative position to the skeleton. In total, the dimension of Vi is 6 plus the number of joints j. Then, the features of each node are transformed through a nonlinear feature transformation module. The module consists of linear layers followed by nonlinear activation and normalization. By this features mapping process, the features are transformed into normalized high-dimensional features that could provide rotation and translation invariance in some degree with enough training data. Next, we input the obtained features to the network to approximate the corresponding correction. There are some challenges for training models to realize this approximation. First, the mesh geometry is arbitrary and its features are complicated, so how to deal with this data and how to map it to the nonlinear offsets. Second, for the huge number of features, how to make the training easy to converge. Then, if we use a deep network, how to resolve the gradient vanishing problem. Regarding the challenges above, our proposed network DenseGATs has 2 main technical contributions: GAT blocks and their dense connection pattern. Let's first take a look at the GAT block architecture. To deal with arbitrarily structured mesh graph data, our method uses GAT blocks for effectively learning mesh features. Specifically, it consists of 2 streams. The graph attention-based aggregation stream is used for computing the hidden representation of each node by aggregating neighboring features with different weights. In addition to this, we also introduce the self-reinforced stream for increasing feature multiscale expression that linearly maps the individual features of each node. In this way, the GAT block can effectively compile information on complex graph features from neighboring vertices as well as information on self-features. We use FGATB to represent the process through one GAT block. Due to the complexity and the large amount of features in our mesh graph, we need to apply very deep networks to benefit from their advantages. However, for training deep graph convolutional networks, the problem of gradient vanishing will become more serious as the number of network layers increases. To address this problem, inspired by DenseNet, which is used in CNN, we introduce dense connection pattern to densely connect our GAT blocks for further training deep layers. If the layer of the first GAT block is L, After MGAT blocks, the result is fusing all the intermediate layers outputs. We refer this architecture as dense module. And this is the overall structure of our DenseGATs. There are 3 dense modules, in which comprises 6 densely connected GAT blocks. Between 2 adjacent dense modules, we adopt 1 GAT block as the transition. This operation plays the role of information integration. To evaluate our proposed method, we train the network with 125 characters with different customization and animate each of them with 8,500 poses. Then, we test the trained network by using 20 characters with random motion sequence. We first show the result of the correction from linear-based rough deformation to nonlinear one. The test character is animated with dancing motion. It could be easily seen that the areas with large errors can be well corrected, and the result deformation become more plausible and realism. We also provide an intuitive demonstration of the prediction error compared with the ground truth. As expected, the network is able to generate visually plausible deformations without noticeable artifacts. The trained network can also improve the detail deformation. We take the characters with Gongfu motion as an example. The approximated results by our network can correct the artifacts of volume loss in the region of elbow. This correction is end-to-end predicted by our network without need of traditional manual weight modification. We also provide a comparison with other 4 different network architectures. We evaluate the prediction distance errors. The first is the result approximated by our DenseGATs that almost deformation could be well predicted. Then, we evaluate the architecture of the original GAT, the neural skinning network, and our DenseGATs without self-reinforced stream and without the dense connection pattern. In contrast, with our proposed network, the best prediction result can be obtained thanks to the operations of self-reinforcement and dense propagation. For such an example character, the timing for approximation with our method is about 31 milliseconds per frame. To conclude our work, we have presented a DenseGATs network that leverages existing well-designed skinning features of characters to accurately predict deformations for new characters. Our approximation is an end-to-end process that can directly predict each vertex deviation in each animation frame. Our GAT blocks and dense modules allow for efficient utilization and transmission of self and adjacent information through our network. There are also a few limitations and potential improvements that could be addressed as future work. First, the network generalization ability is substantially dependent on the character mesh information. In the future, we would like to design more effective feature representation method to express the graph information. Second, our approximation mechanism cannot be applied to dynamic behavior simulation. Finally, we train all characters together and do not consider the material attributes of different garments or skin. To perform perfect visual effects of deformations, future work can independently train networks with different materials. Thank you for your attention.